Do we have?
There you go.
There we go. And mine says the video has ended. So I'm just going to go ahead and
It's up.
it's up. Okay.
Yeah, it's a different screen now.
Yes.
It's not the same screen that you were on before.
Yeah, my computer's not finding it, so I'm just going to go ahead with the video. Anyway, sorry about the technical difficulty, folks. As you all well know, if you use a computer, sometimes we are at their mercy rather than controlling everything they do. I think when my audio went out, we were talking about the exciting Axion particle and how folks go about seeing these things. Whenever you're talking about particle physics or astrophysics, where we're talking about dark matter, we're really looking for subatomic particles. We're looking for very, very small things, which are sometimes very short-lived as well. And many times, either something is so short-lived we can't actually hold it long enough to examine it, or if it's very hard to detect, like a neutrino, we don't actually detect neutrinos themselves. We detect what happens when a neutrino collides with an electron in a water molecule. And so when we're looking at axions, we are in fact looking for the decay products. This adds another level of uncertainty into the equation. The Xenon experiment in Italy announced detection of something like a dozen potential detections of axion particles. Now, as I mentioned before, when we build an experiment like this, we are looking for things at the absolute threshold of detection. We are building the most sensitive instrument we can, and almost always in these sort of situations, we're looking at an instrument, oh, the new and improved special instrument should be just able to detect certain signals, and that's what we're doing with axions. We have this Xenon experiment in Italy, which should be just capable. And because we're looking for things at the threshold, if you think about tuning an AM radio and you've got a station you can just sort of pick up, and if you listen closely, you can make out the words, that's the level of signal to noise we're talking about here. And so this is a disputed result. There are people who are scientists who are saying, no, I don't think this result is valid. And there are other scientists who are saying, oh yes, we think this is good. The scientists who do these sorts of things get their data, they publish it, and then they ask the scientific community, what do you think? Did we do good? Did we make a mistake? Is there a problem here? Is there some follow-up experiment we should do? And other scientists go through and try to recreate the experiment, perhaps in a novel way. But in any case, axions have been proposed as this new candidate for dark matter. The other item in the news we're bringing in this week is a study that was just published this week. Scientists using the MUSE telescope network, MUSE. They also were looking for axions. And so they had this great idea. Let's look at 5 nearby dwarf galaxies. And if these dwarf galaxies, if we can see by their rotation, they have a dark matter halo, then in fact, if it's axions, the axions should be decaying, and decaying axions give off a very particular optical signal, and so far, they haven't been able to detect it at all, 0. So again, we have contradictory, as often is the case on the bleeding edge of science, we have contradictory results. Time and further experimentation will tell, but for the time being, dark matter and axions are both still a mystery. The last item in the news before we move on today to our regular program is our sponsor, Explore Scientific, is going to be starting a certified pre-owned program, which is exciting news, especially as we approach the holidays. People who want to get into astronomy, who are interested in astronomy equipment, but maybe they're not sure what their budget can hold, or maybe you're just looking to pick up a bargain. As we move forward and launch the CPO program, I can tell you there's going to be 2 things. One, the bargains will not last. These things are at such exceptional prices, they're going to go very quickly. And what's available for certified pre-owned will change as new stock comes in, old stuff is sold. So when we get that fully ready and fully launched, we'll let you know. But in the meantime, we wanted to let you know that's coming. So today's program, can the constants of nature change? And this has long been a debate in the physics community. Are constants of nature, things like the charge of the electron, the Planck constant, mass of the proton, the strong force, the weak force, are all these things constant throughout time? Much of our science is based upon the assumption that these things don't change. The idea that gravitation is as strong as it is, always was, always has been. This unchanging constants of nature has been bedrock of physics and astronomy for centuries. And yet, we've heard of MOND on this program, Modified Newtonian Dynamics by Professor Mordecai Milgram. And one of the things he proposes is that, yeah, sometimes gravitation changes, which raised a big uproar in the physics and astronomy community. No, that can't be. We've always said gravitation is constant. Well, one of the things we look at, and this new research that we're talking about today comes to us from Queen Mary College in London. And scientists there looked and they said, they noted something many other people, including me, have noticed. Gee, the constants of nature are very, very precisely tuned so that life can exist. In other words, if we take things like the gravitational constant, the strong force, Planck's constant, the charge on the electron, Coulomb's constant of electrostatic repulsion, if we take any of those fundamental things and we change them, sometimes by as little as 1,000th of a percent, we're talking 6 or 7 decimal places down the line, then life is no longer possible. The strong force, for instance, if we tune it or adjust it, we wouldn't be here. And so this idea that, gee, the constants of nature are very finely tuned to permit life to exist. Well, how do we explain this? The oldest explanation is from a couple of astronomer and astrophysicists, John Barrow and Frank Tipler, and they are the primary exponents of the anthropic cosmological principle. And we've talked about that on this program before too. The anthropic principle makes several claims. It says, first of all, the fundamental constants are set at the beginning of the universe. You can think of it like a big dice game where you have a big container of dice and you shake them and you throw them down, and whatever the dice come up at, that's what it is for the life of that universe. So Tipler and Barrow, the anthropic principle, they say, gee, if we weren't in a universe where all the constants came up very precisely tuned for life, we wouldn't be here, we wouldn't observe it, we wouldn't know anything about it. We're observing a universe that's finely tuned for life because anything else wouldn't allow life to exist. Therefore, this is the only universe we could possibly observe. And Tipler and Barrow say the universe is sort of a cyclic thing. It's born, it exists, it dies, and then it restarts again. So, according to the anthropic folks, the Big Bang wasn't the only bang. There were other bangs before, there will be other bangs after, and each time we have a bang, the entire set of constants gets reset. So, once you basically say, gee, a highly evolved, self-aware form of life exists, the amount of wiggling you can do, the wiggle room for the constants of nature is indeed very, very small. The new theory is from a physicist, and I'm hoping I'm getting this name correct, Kostya Tratchenko, at Queen Mary University in London. And his hypothesis has two parts. The first, he's primarily a biologist, and he's looking at limits on fluid viscosity. Now, this may seem like a whole long way away from nucleosynthesis of elements and fusion, etc. But in fact, Trichenko says viscosity sets a limit on life. In other words, how readily do fluids flow? Think of a glass of water and a glass of motor oil. Water flows very, very easily, readily, and motor oil does not. We say motor oil is highly viscous, and we say water has a low viscosity. Well, it turns out that if you look at fluid motion in living organisms, things like blood flow, digestion, elimination of waste, all these sorts of things, diffusion of things across cell membranes. Oh, you have blood sugar and cells need it, but you need insulin to transport it. And this transportation of things across membranes basically creates a viscosity limit. If all liquids were the consistency of tar, then life couldn't exist because blood couldn't flow, circulation would be impossible, the exchange, well, just think about what we all learned about how DNA assembles proteins. That requires a fluid medium, and if it's too thick, if it was like corn syrup in the cell, the assembly process would be far too slow for life to exist. It wouldn't work. And Trichenko says that, gee, these constants of nature, things like the charge on the electron, the charge on the proton, the mass of the proton and electron, Planck's constant, these things, says Trichenko, could have tuned themselves later in the history of the universe. The universe didn't necessarily start with these constants at these precise levels. And we talk about how finely tuned these are, the strong nuclear force. When we talk about stars, stars depend on two elements, hydrogen and helium. Both are present in every star. They have to be. Hydrogen is 75% of the mass of the universe. Helium's about 24%. The other things, very small amounts. And so if the strong force were weaker, we wouldn't be able to have helium because we wouldn't be able to assemble the protons to make that atom. And if we can't make helium, obviously we couldn't have nucleosynthesis and go all the way away. But if the strong force were much stronger, what would happen? Then fusion would have been millions of times faster potentially, and all the star-forming material in the universe would have already been used up. And there would be no hydrogen remaining. And if there's no hydrogen remaining, then the whole energy-producing process of stars wouldn't be there for us. So Trichenko, you get down to nuts and bolts, he says there's no need for intelligent design, and there's no need for the anthropic principle, the idea that you just keep rolling the dice until you come up with the answer you want. Kind of the way a 7-year-old plays Monopoly. No, I'm going to roll again. I needed a 7. Trichenko suggests he doesn't call them constants because, of course, if they change, constant isn't the right word. He calls them traits. Okay? What you and I knew in school as constants of nature. He said that they emerge independently and they oscillate or change over time, only eventually becoming fixed. And this is, he says, analogous to a process of biological evolution. So Trichenko is proposing an idea here, friends, that we have these constants and that as they evolve, life goes ahead and exists, and somehow when life exists, that is the best form, and so the constants become stable. Now, if we look at biological evolution and we say, gee, we're talking about, let's say, fish. And very early on, Fish were probably all herbivores, but at some point a predator fish developed and successful traits are passed on. If you have a predator fish that swims a little faster, he eats a little better, he reproduces more often, and this is how biological evolution occurs. The survival of the fittest, the best traits, which are essentially all random in every organism, but the ones that have the best traits are more successful, they reproduce more often, and they become more common in the environment. So his idea says, Trochenko says, we need to investigate. We need to look not in the context of stellar astrophysics, but instead, he says, we need to look in the constants at biologically relevant energies, pressures, and temperatures. Because it's fine to talk about the strong force and how helium is created by fusing hydrogen nuclei together, but that doesn't happen at biologically relevant conditions. It's too hot, the pressure's too high, the radiation is far too great. Life doesn't exist there. So Trochenko says, we need to take a look at biological processes and we need to reinterpret them in terms of physics and physics constants. And he says that fundamental biological processes need to be expressed in the most fundamental units possible. This idea of expressing constants in the most fundamental units has been going on for a long time, and we have a program on the docket for that in future. But Trochenko basically went ahead and he calculated a formula for the viscosity limit. And he created it in terms of simply Planck's constant, the mass of the electron, and the mass of the proton. And so this process of biological viscosity is now boiled down and expressed in terms of fundamental constants of the universe, which I think is very exciting. And Trochenko points out that fluid viscosity reaches a minimum when liquids evaporate. When they flow so freely, they're no longer constrained to be liquids, they just diffuse out into the environment. We call that evaporation. And this transition gives us the local minimum. And Trochenko was able to establish something that he referred to as kinematic viscosity, which is the ratio of viscosity to density. And this, in terms of Planck's constant, molecular mass, and electron mass, which are all basically fundamental units. And he says, gee, we need to take a closer look at this. So fluid flow, absolutely essential at the molecular level. So if we talk about things like molecular transport, you need to get a sugar molecule across a barrier. If you need to get a drug, a chemotherapy drug, across the blood-brain barrier into the brain where it can attack a tumor. If you're talking about normal biological processes like oxygen going across the cellular barrier into your bloodstream, that transition interface in your lungs. And kinetic viscosity is essential for all of these. Fluid flow is also absolutely essential for the macroscopic processes. Things like blood flow, digestive processes, all of these things where we have a non-microscopic flow of fluids and materials. And he basically investigated, he said, gee, how do the constraints, the biologic limits, how do those translate into limits on the fundamental constants, or traits, if you will, of the universe? In other words, what does biology tell us about the most fundamental concepts and the most fundamental measured quantities in physics and astronomy? essentially, Trochenko said, if we look at all this, kinematic viscosity, dynamic viscosity, and fluid dynamics, he says this sets for us both upper and lower limits for these values. So if our fundamental values are fundamental constants, strong force, charge on the electron, charge on the proton, electrostatic repulsion, all of those, if those allow life, they must allow life within certain limits. Now, this has always been assumed by the anthropic crowd. This has always been assumed by the intelligent design crowd. Oh yes, these values are this way because life exists, and if life exists, the existing values must be the right ones. And people have examined what happens if these fundamental constants change. But they examined it in terms of, will stars burn for the right length of time? Is fusion possible? Is nucleosynthesis possible? Can you have a star that lasts long enough based on the rate of hydrogen burning for planets to form, and for these planets to exist long enough and have a stable environment long enough for life to emerge? We've looked at it like that, but nobody, to my knowledge, has ever gone all the way down to biological processes and then said, okay, if these are the biologic limits, let's work all the way back to the fundamental constants of nature and see, if biology exists, what limits does biology set on these constants? I think this would have been a fascinating study, even without the next step, which Trochenko very boldly takes, that, this universe has life because eventually these constants settle into a value permitting life to exist. Trochenko doesn't take up two questions I consider to be essential here. One, what's the mechanism for this change? If you're going to have fundamental constants changing, what's driving that change? If you have any other change in nature, the brightness of a star, the rotation rate of a galaxy, when corn plants emerge from seed in the ground, whenever you have a change like this with sufficient amount of research, you can trace it back and you can say, these are the causes of this change. This is what triggers this change. This is what drives it. And yet, in Trochenko's theory, there's no mechanism at all for how these constants change. The other fundamental thing is, what's the feedback mechanism? If you're going to tune something until it's perfect, well, you have to know when to stop. If you're tuning a guitar and you're tightening the string, ding, 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 you have to know when you're done. If you have learned how to play and tune a guitar or a stringed instrument, you may have had that situation where you're stringing and tightening the string, ding, 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 and then it snaps. There has to be a feedback mechanism. When you talk about biological evolution, the feedback mechanism is generally who survives, the mechanism of fitness. So if you have fish, guppies, which are born with slightly different shaped size fins, the fitness test tells you when you're done, because the ones that are most fit survive most often and reproduce most often. And so that's how that gene pattern becomes stable in the environment. If you have an unstable gene expression, and a guppy was born with a hugely oversized fins that were too hard to move through the body for its little fishy musculature, and so it couldn't swim very well, and it couldn't eat very well, and mates shunned it because you look strange, your fins are really big, and it dies out without reproducing. That gene is not carried forward. That's the stopping mechanism, the feedback mechanism. And again, if you're talking about a mechanism linking the most fundamental things like charge on an electron, strong force, weak force, Coulomb's constant, electrostatic repulsion, all these crazy things. Well, how does, in fact, biology feed back to these constants to tell them, yes, you've got the right value now? Think about gravitation. Gravitation is one of the universal constant of gravitation is one of the fundamental numbers, the fundamental constants, and gravitation is important. You have to have enough so that clouds of gas and dust will collapse and form stars. It can't be too massive or the stars would have all collapsed, burned, novaed, and gone dead. It would be a dark, dead universe a long time ago. If gravitation was too weak, well, the clouds would never quite collapse enough to start fusion. If gravitation changed, how did biologic life, one, get started, and two, how does it tell the wavering constants of gravity, stop, stop, stop? You're at the right place now. Especially considering these changes on the order of 6 or 7 or 8 or 10 decimal places out. We're talking, a thousandth, a 10,000th of a percent or less. How does biology feed these very, very small and precise changes back into the universe? How do multicellular life forms on a planet communicate with the universe in general and say, hey, turn the gravity down a bit. It's not like a thermostat, is it? You can't adjust the electrics in your house. So you're comfortable, you can do that. But for a multicellular organism to influence the universe, not just even the solar system, but the universe, that's an unanswered problem. But what Trichenko's investigation really proves, or really does show, and convincingly so, is that not just fusion, not just nucleosynthesis or planetary formation depend upon these constants, but actual biological life. The argument in the anthropic principle, the intelligent design principle, has always been something like the constants of nature have been set or occurred randomly, depends on which camp you're in. The constants of nature have been established such that, 1, stars could form. 2, nucleosynthesis could occur. 3, that stars would go nova in a way to spread their synthesized nuclei out into the universe. 4, that a second smaller generation of stars, a second and third generation of stars would be born, which would have enough contamination, metals to you astrophysicists, basically everything helium and up for the rest of us, to form planets. How do you form a rocky planet or a rocky moon on which life can exist unless you can form silicates and oxygen and carbon and all the other fun things that we need? Well, the anthropic and the intelligent design crews have all said the constants were established and then life occurs. Now, the Mond group said, well, yes, constants change. Gravity in particular changes, but it's based on how much mass is involved and how big a space you're looking at. You need to have a lot of mass in a really big space, and then gravity starts to change. Now, people don't like that, but Einstein said much the same thing about relativity. Oh, gee, space-time is flexible, it's bendy. You can warp time, you can warp mass, you can warp distances. But, said Einstein, this new physics only occurs under certain conditions, really extreme amounts of gravity. Big stars, galaxy clusters, things like that, and at really extreme speeds, what we now refer to as relativistic velocities. If you're talking about a baseball or a rifle bullet or even a planet whirling around a massive star at a very close distance, you know what? You're still not talking relativistic velocities, where time and space are substantially warped. Mond says something similar, but Tkachenko goes entirely another step. Tkachenko says that, well, the constants were established, but they're not fixed yet. And that there is a mechanism for change, and the mechanism involves biology. And I don't know if I can go quite that far with Professor Tkachenko. It's a fascinating idea, but I think the idea that, in fact, the blood pumping through my body, my digestion, the viscosity of my tears so that I can blink and wipe them away and see through them, all of these fascinating things, that they're linked to these fundamental concepts, these fundamental constants, which were somehow set at the beginning of the universe, and that essentially look deep enough into the heart of a cell, and you see evidence for how the universe was set up at the very beginning of all creation, the beginning of the Big Bang. These numbers were established, and current physics and astrophysics theory says, oh, we can look back until, a few units of Planck time before the Big Bang, where our math breaks down. But at that point, all those constants are in play, and they all work, and they all have the modern values. That's the assumption we go on. And we've not really seen anything conclusive to say, oh, these things change. Now, of course, there's the idea, how long does it take them to change? We have done experiments where we've looked at atomic clocks for a half a century. And we're like, oh, do we see any variation in the rate of an atomic clock? No. No evidence there that constants change. We've looked at things like pulsars, neutron stars, which orbit, and as they give off energy, they slow down. And everything we've measured over about a century says no. Everything we know about gravitation and energy transport is sufficient to explain how pulsars and neutron stars evolve, and we haven't needed to bring in, there's been no need to bring in extra physics to explain, oh, if fundamental constants really change over time, did they do so only in the early universe? Did they reach some evolved state and then stop changing? If so, why did they stop changing? We know why biological evolution stops, because there's no pressure on the organism to change or do better. What, sharks have been around, turtles have been around for hundreds of millions of years. Why? Because their body design is very efficient, very effective. They have no need to change. On the other hand, we've done this experiment. Take a huge population of mosquitoes and spray them all with DDT. Look, 99.8% of them die. Guess what? You've now put pressure on the population, and you've selected only those that are resistant to this pesticide. And going forward, they are the only ones that reproduce. We've heard about antibiotic-resistant bacteria. Oh, we put pressure in the environment. And these organisms change in response to the pressure. The old ones who are less fit die. The new ones that are more fit survive. Okay, how do you put pressure on a constant of nature? Either to change or to stop changing. How is that pressure relieved? What's the mechanism? And although I think from Tkachenko's work, I can pretty much say you and I are made of star stuff. The same fundamental forces that control nuclear fusion at the heart of a star, nucleosynthesis during the instant of a supernova explosion, all of these sorts of crazy things, those constants also control and shape the biological processes that are me, that are you, that are all the myriad organisms of life, animal, plant, fungi, multicellular, microcellular, all of these crazy things. We are all linked to the stars more closely than we think. We are all made of star stuff. So next week when we come back, and by the way, if you're interested in more information, please download the show notes. We've got links for you, and you'll find them at the end of the show notes on the Jupiter impact, on fluid viscosity, and fundamental constants, and on discovery of axions. We've got stuff on all of that. But when we come back, our next program, we're going to be talking about October's partial eclipse. So we're going to be focusing on eclipses over the coming year, and we're going to give you a series of eclipse primers. And our next show, number 81, will be on October's annular eclipse. What's an annular eclipse? Why do they occur? How often do they occur? What's the difference? And how can I observe the eclipse coming up? We'll have all that for you coming up. Next week is our program on October's annular eclipse, and we'll have more eclipse programs leading up to 2024's April total eclipse. Also want to remind you, if you plan to go out eclipse observing, and you're thinking, oh, I'll get a pair of those really cool eclipse glasses. Friends, neighbors, please order them now. Explore Scientific has them. If you're looking, look for solar glasses which are approved, which have been certified. Last time we had an eclipse, 2017, there was a lot of phony eclipse glasses being sold that did not block enough light, did not block UV. People damaged their eyesight. We don't want that to happen to you. Our sponsor, Explore Scientific, has certified glasses. We've taken the coating that we use to screen the sun, and we've put it through a rigorous testing procedure through independent laboratories, and they've certified this film is safe. It's a safe solar viewer, and yes, a little more expensive than the cheapy knockoffs. Yes. Worth it? Yes. You only get 2 eyes, folks. You got to take care of them. Please make sure you get your eclipse glass ordered. Last eclipse, 2017, as we got closer, we were seeing 30,000, 40,000 orders for eclipse glasses a day, and many people were disappointed. Don't let that be you. Get your eclipse order in today. We thank you for showing up and for listening to all our little technical difficulties today, and we'll see you next time on How Do You Know?
Prepare for the solar eclipse on October 14th, 2023 with our exclusive solar viewing glasses. These glasses are not only designed to protect your eyes from the sun's rays, but they're also proudly made in the USA and meet the highest international standards. With comfortable temples and stylish black and gold design, you'll be all set to witness the eclipse in both safety and style. Experience the eclipse with confidence and embrace quality craftsmanship. Explore our solar viewing glasses now, proudly made in the USA for an unparalleled viewing experience.